As promised, we will now go over some examples of problems involving heat. They will make use of the relationship between energy and the change of temperature that was discussed in the previous lecture. The first example deals with a single lead ball that undergoes a change of temperature, and we want to know how much change of energy was involved. There is no need for drawing, so we will go straight to defining the givens. We are first given the mass of the ball, which is converted to kilogram. Next comes the initial temperature and the final temperature. Lastly, we are given the specific heat capacity of lead. We have all the information required to evaluate heat, which is labeled capital Q. Remembering that delta T stands for the change of temperature and that the change of temperature can be written this way, we are now in a position to substitute the numerical values. We reach an answer of 165 joules. This is our final answer. Notice that due to the rule about significant digits for subtraction, the delta T gives 300 degrees Celsius with 3 significant digits. Since all other factors have 3 significant digits, the answer must have 3 significant digits, even though 25 degrees Celsius had only 2 significant digits. Let us now consider the general case of two substances with different temperatures coming into contact and not interacting with their surroundings. Due to the second law of thermodynamics, the flow of energy is from hot to cold. Since the total energy must be constant, the cold substance gains as much energy as the hot one loses. Expressing this concept with an equation gives this, where the subscripts 1 and 2 refer to the two different substances. The transfer of thermal energy occurs until both substances reach a common final temperature, Tf. We can then write their changes of thermal energy in terms of their respective mass, specific heat capacity, and change of temperature. Collecting all the terms with Tf on the left-hand side and all the terms without Tf on the right-hand side gives this. Factoring out Tf and isolating it on the left-hand side of the equation leads eventually to this expression. This is the weighted average of the two initial temperatures. To illustrate the previous situation, let us look at the problem of mixing cold cream into a hot cup of coffee and trying to predict the final equilibrium temperature. We will go straight to the givens and neglect the heat that would be involved in changing the temperature of the container. Otherwise, we would need to have been given the mass of the container and its specific heat capacity. But we have the mass of the cream, M1, the mass of the coffee, M2, the initial temperature of the cream, Ti1, the initial temperature of the coffee, Ti2, the specific heat capacity of the cream, C1, and finally the specific heat capacity of the coffee, C2. This is a case where the formula derived in the previous slide is applicable. Substituting the givens gives this. And after careful consideration about the number of significant digits left after each calculation, we arrive at this answer, 84.8 degrees Celsius. This is our final answer. Notice that this value is in between the two initial temperatures and is closer to the initial temperature of the coffee, since the coffee has a higher mass as well as a higher specific heat capacity. The same principles of reaching a common temperature and keeping the total thermal energy constant can be used to measure the unknown specific heat capacity of an object. Let us illustrate this problem with an example. Let us extract the givens from this problem. We do not know the specific heat capacity of the rock, but we know its mass, M1. The rock is first forced to take the temperature of boiling water, which is by definition 100 degrees Celsius. This is the initial temperature of the rock, Ti1. The rock is then moved into a known mass of water, M2, with a near freezing temperature, Ti2. The rock cools down in this cold water until the water and the rock reach a final equilibrium temperature, Tf. We are also reminded of the value of the specific heat capacity of water, C2. We are looking for the value of C1, and it is easier to start back with the equation expressing that the energy loss of the rock is equal to the energy gain of the water. We next replace the Q's with their respective expressions in terms of mass, specific heat capacity, and change in temperature. Isolating for C1 gives this. Replacing the variables with their numerical values gives this. The use of a calculator leads to a numerical answer of 900 joules per kilogram per degree C. This is our final answer. All the examples in this lecture were about thermal energy changes of substances that underwent changes of temperature but no change of phase, such as melting and vaporizing. Since changes of thermal energy are not only about changes of internal kinetic energies, but also about changes of internal potential energies, we need to have a look at some possible changes of potential energies to have a more complete understanding of thermal energy. This will be the subject of the next installment.